Good morning, everyone. Today is November 11th, 2017, and this is the John Chappell Natural Philosophy Society Saturday Science Chat, where we, as the dissident science community, can discuss alternative theories to science. And so please visit our website, naturalphilosophysociety.org, and or our forums, and like us on Facebook. And as members, you can participate in conferences like this and our blogs. So today's topic I have entitled, What's the Matter? In our previous discussion, we had ended up trying to discuss the nature of matter. And so a lot of people in alternative science have lots of ideas about that. You know, some people think they're made out of this or that substance. They're like little balls of energy, or that there's vortices or toroids, or, you know, there's a lot of attempts in order to basically take mass and, I would say, remove its materialism. But, you know, things like saying that an electron is made out of a wave, for example, or saying that all matter is made out of some kind of wave is a very popular alternative science idea. So I wanted to discuss that. And so I had just started the discussion off this morning with Bill Lucas. And, you know, we're discussing the nature of mass. And, for example, when we are trying to determine the orientation of a crystal, you know, if you have some nice crystal that you grew, you may not necessarily know which way the crystals are oriented. Let's see here, we got a big echo coming in here. There we go, let me mute that, okay. Although one of the things that we observe with crystals is that now if you grow a nice crystal, you know, it'll come up to be like a nice cube, or a rhombus, or even a octahedral. So in some ways, you know, I believe that shape reflects what the microscopic arrangement of the individual atoms are. So let's say, you know, if you're growing a salt crystal and it comes out to be perfectly square, then I think to some extent, if you went down and saw exactly what the individual atoms are doing, that they're effectively square. So, Bill, why don't you go ahead and continue on with your thoughts? You were saying something about, you know, the nature of what we think we're seeing when we're like doing experiments on crystals.
What I think might be more positive contribution would be to talk a little bit about the history of the concept of mass, because it has a very old history.
Are we talking about mass, or are we talking about matter? And
well, mass is a property of matter.
Yeah, so it's a property. It's not actually matter that we're talking about, but the property.
And so the question is, what causes that property? And that question was addressed by the most ancient of natural philosophers. In fact, the oldest natural philosopher that we know of who addressed this issue was Moses. It's not recorded in the Bible, but it is recorded as it was received along the trade routes. You know, Israel was in the kind of the Middle East, which is on the trade route from Asia to Europe to Africa. And so a lot of information flowed along that trading route. And the Indian Jains in 700 BC and the Greeks also, their historians of natural philosophy recorded that Moses did his work before the Trojan Wars, which made him, it was all, by the time the Greek philosophers started doing work, it was almost 1,000 years later. And so they were doing their thing. But the historians say that they never, for the most part, gave Moses credit. Because
let's not get too much into the history part and more into the science part.
So anyway, what was the concept that Moses had? Moses had that all matter was constructed of monads. And the term atom for uncuttable refers to monads. The monad is not the chemical atom. It never was. But modern science has rewritten the history of science to make it the chemical atom. But we know that the chemical atom is cuttable because it consists of protons and electrons and neutrons and stuff like that. And even the protons, electrons, and neutrons have a structure, and they're made of something else that's smaller, which we have called quarks and other particles. And so the question is then, well, how does that fit in with the oldest concepts in natural philosophy, that all of matter is made of monads? And there are only two types of monads, a monad and an antimonad, or you might say a positive and a negative particle or something like that. And all elementary particles and all the subparticles, quarks and stuff like that, within elementary particles are constructed of something smaller called a monad. And the monad was not completely defined in a form that we would like, at least not that we had passed on to us, but the monad had no property that they knew of that could be measured directly of the monad. They claimed, the ancient philosophers did, they claimed that all matter was composed of geometrical structures of monads. And it's very interesting that over the top of their, what we would call universities, they called them, I can't remember the name right now, but anyway, the leading philosophers, for instance, in Greece, they would have a sign that says, "Let no one ignorant of geometry enter here." And the idea was this monad structure. If you didn't understand geometry, you couldn't understand the nature and the qualities of the universe. And so that's how they came up. And they claimed that properties like color, whether it was a liquid, a gas, or a solid, or a fire, or plasma, was determined by the structures that were present, and that all properties of matter, were just dependent on this structure. So geometry determined everything, and so that was the concept. So, and when Einstein came along, you wouldn't believe this, but he was taught this when he went to college, because every university in Europe and America taught this before the year 1900.
So the idea is that the ancients didn't necessarily know what a monad was, but they definitely believed in it. and that everything we see is just a geometric rearrangement of the monads, and
That's right.
that's it.
Well, then we started doing experiments related to this, and the first person who received a Nobel Prize for working on this was Arthur Compton, and Arthur Compton discovered the Compton wavelength of elementary particles like an electron, a proton, etc. And so these uh, wavelengths, what did they mean? We talk about, well, an elementary particle can be both a particle and a wave, because now we've measured the wavelength and we can see it. We can do experiments to confirm it. Uh, but what does it mean? And so Arthur Compton worked on this all of his life, and his last graduate student, his last chance to have someone who was his slave to do these experiments, was named Winston Bostick. And Winston Bostick showed how to make a structure, which he called a plasmoid or a soliton, of the electromagnetic field. Now, this field had no charge. It was just a field. It had only the properties of a field. And so he was able to make a structure which was in the shape of a toroidal ring. And he wanted to know how strong, how permanent is this structure? Can it be cut? He couldn't find any device that could cut it. He put it in a nuclear reactor with all kinds of elementary particles going around with tremendous energy, and the elementary particles were coming apart in there, but this toroidal ring made from the electromagnetic field survived all of that when none of the other particles could. In other words, it was more structurally strong than any known elementary particle, including the electron and the proton. And so he published a paper showing the results of his experiment, and he also showed that this idea of a field was something that was common to many theories or areas of science. For instance, the field controls fluids. The field controls a lot of things in astronomy that we see, and so it has very long range, and so that was what he contributed. But then another person came along who did some fundamental experiments in electrodynamics, and he found that there were three types of fields of electric, three types of electric and three types of magnetic fields, and he measured 14 properties of these fields and showed that each of the total 6 fields for electromagnetics had different properties. Like one of the properties that one of them has is it cannot be shielded. That one type of field. All the other types of electric fields can be shielded, but one of them can't. And that wasn't known before. And so, but the property that he measured that was the most significant, I think, was that the field is not made of components, and it is a continuous type of thing, and it has a tensile strength. And that's something that wasn't really appreciated or known before that. So
why don't you explain what you mean by tensile strength? I'm not quite sure that people would understand it in this context.
Okay. Well, if I have two charges and they exert, one's plus and one's minus, and they exert a force on each other, how is that force communicated? If there's matter around, it's communicated. If it's in empty space, what we call a vacuum, it's communicated. And but there's no matter there that you can see. And so the question is, how could that happen? And the answer is from these measurements that were made by that the field is a continuous substance with tensile strength, and it extends to infinity, as far as we know. It doesn't. There's nothing that limits its extent, and so that is a very interesting thought. And how does it affect our concept of matter? Well, one way to look at that is that all matter is made of electromagnetic fields, not charges with mass, but electromagnetic fields. And we could cause the minimal structure of the electromagnetic fields, we could call that a monad that Moses used, or we could call it a soliton, which is what Winston Bostick called it. And we could say that the structure now, when we make something with multiple monads put together in some geometrical combination, that the structure now can have oscillations of the field. We have oscillations of the field when we do radio transmission and all that kind of stuff, and broadcasting. And these oscillations have energy, and they affect the forces between two structures. So, for instance, when I have structures that oscillate, I can calculate the electromagnetic force using the Maxwell's equations, and I find out there's a net force, and it's attractive between electrically neutral bodies, and that's the force of gravity. And I can derive big G and all of that, define mass and all that, just in terms of the energy of vibration of this structure of monads or solitons or whatever you want to call them. And
so are you saying that that the monads themselves are the very first thing that gets constructed out of this electromagnetic field? Is that
right
accurate?
Right. And there's some videos on the internet that are kind of interesting. They show you how to use a very weak field with very little tensile strength, which we call water. You can move a plate back and forth and make them. And it's interesting, you get two monads or solitons in the water in the shape of a ring when you make it with a plate. And what you're doing with the plate is you're just disturbing the field.
How do you spell that name, Bostick?
Bostick, Bostick. And the first name is Winston, Winston. And his most famous paper was published in 1991, which it has to do with the shape and structure of the electron, the morphology of the electron.
Back to our fundamental question of our discussion today, which is what is matter? So it would be accurate, in your opinion, to say that matter is something which is formed out of the electromagnetic field.
Right. And charge is a property of that structure. Mass is a property of that structure. Color is a property of that structure. So all the properties of matter are determined by the geometrical structure and vibrations of that structure.
Now, you mentioned that there would be like two monads. There'd be like, a monad and an anti-monad. But now, Do you
That's
have any
because
conception of how that is? Those are built out of, the generic electromagnetic field?
they're just they're just structures in the field. Now, mathematically, when we look at the force between two of these structures, we approximate that using a concept called charge. But this idea was that charge is something we have made up, and it's not something that is separate, different from the field. What the experiments seem to show is that charge is just a mathematical approximation, which works pretty well to the concept of field. And we have a 1 over r squared force between two charges, and we have a 1 over r squared force between two monads or solitons. And but as Winston Bosick would say, there was no charge there, and that charge is not a something that you can verify by experiment exists in a soliton or a monad.
Are there about as many monads as there are particles, say, in a billion, cubic miles or something? In other words, how many of those things would you say are in the seeable universe?
Well, it's very, very large.
Okay, in other words, okay, the reason why thank you very
There we
much.
go. There we go. We got it.
Because frankly, I have never heard of the guy, and I'm just kind of looking at this. Okay, and
Yeah, this book is available on the internet. I'm not exactly sure where I got it from, but
okay, thank you.
This is just the paper. I think this is a copy of it. It's kind of I think it was like a Xerox or something because it's got some lines in it which weren't in the original. But yeah. So anyway, what in describing what is mass and what is matter, this type of approach would say that matter is structures in the electromagnetic field, and these structures are monads or solitons or whatever you want to call them, but they are structures, and that property of mass, you just have to have more than one structure in an entity, in a piece of matter, and the multiple monads, for instance, would be able to vibrate with respect to one another through the tensile force that the field gives. But what you learn is that what we call a particle, such as an electron, does not have a hard surface or anything like that. It extends to infinity, but it's centered physically at one spot, but it doesn't have an edge. And so just like when I have a hurricane or a tornado, I have a place that we call the eye of the tornado or the hurricane, and I can identify that, but that's not the whole thing. I have to know about all the clouds that extend for 1,000 miles in every direction because they all participate, and then I can actually see that. Particularly if I'm in space with a satellite and I can look down, I can see that overall structure. And basically, the same thing is happening here with the soliton or the plasmoid. I think he called it plasmoid. That in this paper, but
has he discussed the plasmoids in this paper?
Yeah, I think so.
Because,
Oh,
we see a
this
lot
is,
of
wait, is
diagrams.
this a book that you've got?
This is from the International Journal of Fusion Energy, January 1985. It's relatively recent.
Okay. Yeah, well, that other one, this is a second paper, I think, or it looks like it's a chapter of a book or something. And but yeah, so anyway, this is one approach, and the claim made here is that this approach is based on experiment. It's not people's opinion or ideas, but it's uh, based on experiment. And so, so that's something that we need to look at and see if it can be challenged or if it is really based on experiment. And I went to see Winston Bostic at New Jersey Institute of Technology and spent a whole day visiting with him and talking to him. He's passed away now, I think. But anyway, this was in the 1990s, and I, you know, I was interested to meet him and to talk about his ideas before he passed away. And so that's one concept. The other concepts, when you start thinking about what is mass, um, we have a number of elementary particles that have no mass. And so how can that be? What are they made of that has no mass? And so this idea that mass is an inherent property of the building blocks of all matter fails when you see the experiments on elementary particles. It's not just one or two elementary particles. If out of the 400 and some that are projected to exist, probably 100 have no mass.
What are some examples of that? Because I thought only the photon was the only one that didn't contain any mass.
Well, the neutrino, we've never been able to verify it has any mass. And there's three types of neutrinos. And most of them are among what I call the more exotic particles that different theories of elementary particles have required that exist in order for them to explain the observed data. So, and neutrinos are only indirectly found, but and photons are the easiest to see, and so yeah. So anyway, that's kind of the background there, and we have this debate going on in the scientific community. What is mass, and how is it? Why are there elementary particles with no mass and elementary particles with mass? And what determines the mass? Now, if you're familiar with the standard model of elementary particles, you would know that there's different versions of it, and they have between 19 and 29 adjustable constants representing unknown physics in their theories currently. And they're not based on solitons and monads and stuff like that. They're using strong interaction, weak interaction, electromagnetic forces, and all that sort of thing in their theories. Whereas in the work that I've done, I've shown that the recent measurements of the 3,500 nuclear isotopes to 8 significant figures has removed all the data that we have that there is a strong interaction force and a weak interaction force. But everybody's keeping their mouth shut.
That's right. All of that strong force stuff, that's a bunch of hooey.
It's in the data that NIST has on their website, but nobody wants to talk about it.
Okay, Bill, so we have...
Bostic has a website, It's indicated at the lower end of the chat box.
All right. You put in a, he's got still, he has a website?
Yeah.
PlasmaUniverse.com. Is that what it is?
Yeah, plasmauniverse.com. Not the other links that I've given. It's the last one. And he is mentioned there. He's also mentioned in Wikipedia.
Let's see here. I can't reach plasmauniverse.com for some reason. Oh, yeah. Okay, you have a correction in here. Let's see. Get that right one in here.
Only the last one. The other ones do not work.
Okay, so this is...
Bill, this is Harry Ricker. I got a question for you.
Okay.
Bill?
Yes?
A question?
Go ahead.
Go ahead, Harry.
You've been exchanging some mails with Roger Ryden, who had sent me a copy of it. And Roger seems to be of the impression that you're denying the existence of neutrons. Is that correct? I mean, I'm somewhat confused.
The neutron as an elementary particle, with accelerators, we can make them, and they do exist. But there is no evidence from the decay of nuclear isotopes that neutrons exist. If neutrons are making up the nuclei and they're splitting up,
okay, so that's your position.
They should be coming out in almost every radioactive decay, but they don't.
Well, I think it would be clearer to say that they don't exist as an identifiable particle.
Well,
right?
They do outside the nucleus.
They're given their properties that we observe outside the nucleus.
Okay, so
there doesn't seem to be any evidence of that thing to be actively inside the atom as we can see it as a whole. There's nothing in there that has those properties. Right?
You know, it's interesting. Inside the atom, the more complicated atoms, Rutherford may have been all his life satisfied with a so-called proton and electron combination in a nucleus that neutralized each other, and not going with a neutron entity as such in the nucleus, but rather kind of a proton that was attached to a neutron. I mean, a proton that was attached to an electron, and thereby seems to simply behave like what we call a neutron. And I've seen a little bit of evidence, so to speak, that that does have some merit. But I'm not going to assert anything definitively beyond just that point of curiosity and interest.
In fact, it would be fair to say that in physics everything is a wave, because when particles like the electron were...
Yes, Alistair, you're trying to speak. You're coming in very weakly. Can you speak up? Get closer to your microphone. Much better.
I think that the question that we're kind of hovering around is divisibility. So we're trying to get to the root of what is or is not divisible. So it's not a question of does the atom exist? We understand it does, but it's divisible. The same thing with the neutron. We understand that the neutron exists, but it's divisible. And so what we're getting at is there anything that physically, substantially, persistently is non-divisible, a fundamental piece? And when we talk about fields, are we talking about fields that are physical? Do they exist? Are they divisible? And let's cut to the heart of the matter and ask the question, is there something that is the smallest that is non-divisible?
That's
Or
what
is,
Winston Bostic did, the experiments to show that.
and so what, cutting to the heart of it, what does William Bostic assert is the smallest non-divisible thing?
He calls it a plasmoid or a soliton of the electromagnetic field, and you can photograph it, you can perform experiments with it, you can put it in a reactor, you can mount it on the end of a prong, you can do a lot of things, and you can show that it has greater durability than any other known entity in the universe that we know of.
Does he have a picture of it?
Yes.
Let's see a picture.
I don't know where if it's in this article. I don't have control over that. But you can photograph it in certain circumstances, and it can be different sizes. There's not one size to the plasmoid. And he worked with the people at MIT and made a jet engine out of a plasmoid. And what he did is he put a prong in there, and the plasmoid would stick on the end of a metal prong, and then he pumped energy into that, kind of like we would do with a microwave, but it's electromagnetic energy, and he put it up to millions of degrees now, and then he allowed air into the engine, and that air picked up this energy that was in the soliton and made the hot air that came out the back of the engine, and they made a jet plane. And this was done at MIT by the people at MIT in conjunction with him. And they demonstrated that plane by flying it around the world. And they had the Department of the aviation airlines, they had the Department of Defense, they had NASA, they had a lot of people there watching it. They flew it at Mach 17, which is very fast, fast enough to go to the moon. And they showed that it could be used for space travel and that it could be used for commercial airlines and for military use. And you would have a great capability. And particularly if you used a type of generator that uses electromagnetic energy from the sun, you do not have to have a fuel. So you could fly to the moon, you could come back from the moon, but you do have to have some kind of gas like air to heat up to give you your thrust from the solenoid. And the solenoid, this soliton could be heated to tremendous temperatures that would cause a nucleus to come apart, but doesn't cause the solenoid or the soliton to come apart. And so that was his evidence that he had. And there you can see a certain kinds of pictures in some of these things, some of these articles of things that he has photographed at the time. And what he wanted to do, this was what the motivation is, he wanted to make a structure out of these plasmoids or solitons that could contain controlled thermonuclear physics. Because one of the problems we have with using that for energy is that all materials disintegrate when they're around it long enough, and so you have to keep replacing things, or your structure for holding your nuclear power generation just disintegrates. And so that was his goal. He never accomplished that goal because he couldn't figure out how to make the kind of structures he wanted. He thought he could make big structures like a bottle, but he never succeeded in doing that. The only structures we know that you can make are the structures of an elementary particle or an atom or a molecule. We don't know of anything else. And some of those, like atoms and molecules, are not very strong. They can disintegrate. And so he found that only the basic building block had the strength in it.
Well, I seem to have found some pictures of his plasmoids here, at least of them. These
Franklin, Franklin, do you have any references or any internet sites that document that flight that you're talking about, that aircraft?
Well, he doesn't. I think I may still have some. That was done in the 70s, so it's been a while. Before the internet. So
I was just concerned because 17 times the speed of sound is over 13,000 miles an hour, which means that you could circumnavigate the globe in about 2 hours and 17 minutes.
That's what they did.
And the challenges are that I may have worked with some of the highest flying fastest aircraft in the 70s and 80s, and most people are familiar with the SR project. Well, the leading edges of the chimes are all composite because they glow between 600 and 700 degrees at 2185, which is Mach 3.2, and the friction from the compression wave in front of them creates so much heat that we have to use an all-composite material. And when we worked on the XP2, which is the Aurora project, that aircraft was limited to Mach 7 because the materials, the composites, we didn't have anything that could withstand the heat from the compression. And the destruction that occurred from what you would consider a bow wake was so significant that even at 82,000 feet, the damage that was occurring on the ground when the Aurora was at just almost 7.1, there was already damage occurring at the ground from 82,000 feet. So if they were publishing that it was 17 Mach 17, I question that because to get that high enough to not have the disturbance reach the ground that we were experiencing with the Aurora project and the superheating that occurred in both the SR and the Aurora projects on the leading edges, that would cause the aircraft to disintegrate due to the heat, the same way that just a vehicle re-entering at significantly slower speeds into the atmosphere, where we have to put expended carbon fiber tiles to protect the aircraft itself. They would have to fly so high that there's not enough. The density of the air is so low that you cannot develop that kind of thrust. So I would love to see that article because thrust is achieved when the heat energy causes the orbit of the electrons in which the air molecule that the energy is imparted to begins to accelerate, and they expand and they push the adjacent molecules away like a big guy in a bus stretching out his arms. And it's that expansion of the orbit of the electrons around the molecule are what caused the thrust, and the rate of that expansion in the way, the capacity to impart the heat to cause that instantaneous or near instantaneous expansion of the velocity of the electrons orbit and their radius of their orbit to cause the others to be pushed out. There's a point at which the atmospheric density is so low that you can no longer achieve certain thrust at certain altitudes, and that if the density was sufficient, the equivalent of what you would see is, we call it a bow wake. But if you've ever leaned over the front of your fishing boat and noticed that the wake that goes in front of it are dragging your fishing line through the water, and notice that there's lines that precede your fishing line as you're moving it sideways, that's that bow wake also prevents the air on an SR from, because of the sheer design of the aircraft. Once you go a little bit faster than that, it prevents any induction into the J58s. And that's why the pointed nose cone is on both engines. It's to pierce the wake so that you don't starve the engines. But there's, I would really like to very much see that article, because those are just a couple of the questions I have with, if they're claiming those type of velocities, it'd be interesting to see.
This is not published in an article, but your comments are very proper, and they couldn't. This plane they were using was a surplus plane, I guess you would say. So it wasn't the best in terms of structure and material for going very high speeds. It was designed for lower speed. And but by taking it high enough into the atmosphere, they could show the speeds they could do. Yeah, you're right, and they couldn't do these speeds too long at the very high velocities because of things like heat. But as far as I know, in talking to Winston Bostic, this was a demonstration. It was considered classified at the time, but I don't know. There may be someone that has that, but the response that Winston shared with me was that NASA was not interested in this solution because you will really like this. It didn't cost enough. No, they didn't want to admit that you could go to all the planets in our solar system for tens of thousands of dollars instead of billions. And they didn't want to admit that you could put satellites up with one of these planes and, do one every day or two. You could put another one up. They didn't want to admit that. And the airlines, they would never have to refuel a plane. They would just pick people up, fly, pick people up, fly, and land, And there was a lot of that going on. And so the project got killed because these groups were financing the research at MIT that produced the plane. And so it was an interesting experience, and I don't have as much doubt about this as many people, because I invented something myself. I invented the super microcomputer, and I replaced over 500 computer centers in NOAA with one or two super micros that cost $8,000 a piece. And after I finished that, saving many billions of dollars for NOAA, the head of NOAA told me, if you don't leave, we're going to fire you, because the government is not about saving money. They were used to getting kickbacks from all the big contracts for the computer centers. And when you put an $8,000 one, you don't even need a computer center. You can put it in a closet and it'll work for years. In fact, if you watch TV and you see the satellite images, those are going through my super micros, which are 40 years old, and a better computer has not yet been made. But they didn't want to admit that, but they're doing it. They're using it, but they wanted to get back to contracts and get back to kickbacks. And that's what the head of computers at NOAA told me. And so I went to work for a Census Bureau with computers, and they said they wanted me to work for them. They didn't want any of my super micros. They just wanted me to do applications for them. So that's a little personal experience there. But yeah, I understand what you're saying, and it's not trivial. You've got to do a lot of things to optimize, and the one at MIT was just a demonstration of what could be. And I've never seen anything written about it.
Probably still classified.
Yeah, it may still be classified.
Or still just basically ignored.
Well,
I mean, it sounds so fantastic. If anyone actually ran into it, they'd probably just say, that can't be true, and go on.
Yeah. And so.
It's like spotting a UFO. It's like.
Right.
Getting back a little bit to mass and matter, and what is mass and matter, it does appear to me that there are entities in the universe, like the concept of a neutrino and other things, possibly a photon, and other action that I'll skip describing for a moment, and just say that yes, it appears that that mass does disappear, as like, for example, in the decay of neutrons, sometimes free neutrons, and we don't find mass, so it's assumed that the mass has disappeared by many people and has been converted to something called energy, but they deny that the type of energy that it converts to has mass. But I think there's another alternative that you don't hear very often, and that is to reassert that the conservation of mass, and just say mass has disappeared, but we can't find it. It has disappeared into some entity or something, and it is simply hard to find. In the worst case, it might have been found, but people do not realize that it has been found, because their definitions are not as precise as they should, and their interpretations are not as precise as they should be. So it's interesting that when Einstein wrote that a body loses mass when it gives off radiation, and the amount of mass that the body loses is equal to the radiation energy divided by c squared, that was not officially, in my view, that did not consist of proving or even strongly asserting that mass ceases to be mass and becomes energy. And of course, even if one accepts that, then they have to accept that energy, under certain circumstances, can reincarnate itself as mass, maybe when it reaches the target. Anyway, so I just want to emphasize that the traditional idea of mass is not accepted by most modern physicists who believe that mass becomes something other than mass, energy, and then energy transforms often back to mass, which is a so to speak, a denial or violation of an earlier view of mass that existed, I'd say, certainly from Newton's time to around 1900 at least.
Yeah, so what's with the, I mean, there's a very common idea that because we have this equation E equals mc squared, and the term mass energy equivalence, that mass is somehow energy, and that what we see as an atom is like a miniature nuclear bomb, right? That somehow that can all be magically turned into its equivalent energy, which would be a lot. So, I mean, the question is that, what is that atom really made out of, such that it can like release this energy? I mean, is matter a ball of energy? Because I know some people might say that.
The Russians have done a series of experiments that I find quite interesting. They have measured the force of gravity on a brass cylinder as a function of temperature. So what they did is they isolated this brass cylinder electrically and everything they could do, and then they raised the temperature, and then they measured the mass by the force of gravity with it. And what they found was that if you start out at, say, room temperature, as you raise the temperature of the brass cylinder, the mass goes up. It's sort of in conjunction with E equal mc squared. But then at a certain temperature, it drops a certain amount. And then it starts going up again. And at a higher temperature, it drops again. And this experiment has been reproduced in many laboratories in Russia and other countries. And if you say that mass is related to some kind of energy in the brass, then the various modes of, say, vibrational energy that could be inside of it some of those modes are removed when the temperature gets too high to keep that structure intact within the crystalline structure of the brass. And so anyway, that experiment seems to say that something that could vibrate and have internal kinetic energy is being lost as you raise the temperature. And even though it's still a solid, not a liquid, and that sort of thing. And so that kind of on a macroscopic scale seems to be compatible with this microscopic idea that within an elementary particle or something like that, the vibration of the monad structure is what produces the mass of that particle. And if it doesn't have the right kind of geometrical structure, it won't have a vibration.
Can you give any sort of reference so that one can look up possibly that article or some reference to the article in a formal way?
Yeah, just a second. I'll look up my book. It's published in my book, The Universal Force, Volume 1. But I've got a copy of it here, so let me see if I can get it.
All right. Why don't you look that up? I mean, there's always questions that come to my mind, which is, if I have a wind-up toy and I wind up the spring, does that, have more mass than when it's unwound? I mean, clearly it has potential energy in it. But just for a couple minutes here, I'll expound on what I think about what's going on here. So I'm going to leave my moderator role and step up on my own soapbox. And I'll comment on, what Bill was saying. Like there's a concept of a monad and anti-monad. Now, I can get onto that, except that I don't think mainstream science is you know, that's not very satisfying because we just still don't know what that thing is. So in my own opinion, though, I would claim that the monad and the antimonad is simply the electron and the positron. So I think that kind of matches what we're looking for, is that we're looking for some fundamental particle that is uncuttable, as we had mentioned. And I think so far as the mainstream is concerned, we have not found the electron to be composed of anything. I mean, some people say, well, we have quarks, but definitely the mainstream does not say electrons are composed of quarks. Whatever quarks are, there are no quarks in electrons.
Franklin, I disagree.
But that is, Franklin has described the mainstream position correctly, that electrons are regarded as not composed of quarks, and to be kind of a super fundamental particle, elementary particle to them is. Anyway, go ahead.
Yeah, but I would think that if you substituted for monad the positron, the electron, then it could get behind this idea that everything is made out of just geometric arrangements of positrons and electrons. So, say in my view, I don't believe that quarks exist at all. I mean, the only thing that I feel that they have evidence for is that things like protons do contain 3-point particles. And if I stick with my guns and say that everything is just a geometric arrangement of positrons and electrons, then that leads me to the conclusion that a proton is nothing more than 2 positrons and 1 electron.
Can I put a remark?
Those are the 3 objects that I would say.
I see Franklin Hans has raised his flag.
Yes, Hans, go ahead. What were you going to say?
I have tried to promote several times in these discussions lately a paper that I wrote about rediscovered dark quanta. These are very tiny excitations of the field that we call our living space. And these, in fact, are shock fronts, very tiny shock fronts, because they are triggered by point-like actuators. And only 2 kinds of shock fronts can exist, that are 1-dimensional shock fronts and 3-dimensional shock fronts. The 3-dimensional shock fronts, these things have a bit of mass, because they, when they are integrated in time, then they have a bit of volume, and the environment, the carrier, is a bit extended in its volume. It's deformed by this spherical shock front. So excitations, vibrations, in fact, of the field can have mass. They are the tiniest quanta that exist, and they constitute all elementary particles. This is the way that elementary particles get their mass. It's written in the paper Rediscovered Dark Quanta that I've put somewhere on the top of the chat box.
All right. Well, people can look at that. Although I would say, from my own opinions, that I'm extremely, extremely skeptical of the idea that matter is made out of shock fronts or any kind of wave phenomenon. Because we see wave phenomenon as being very fleeting, and it must be something. It must be something. It must be something that is going to deform our living space, is going to deform the continuum. So it must be directly interact with that continuum on a very low scale.
I have an experiment that you can perform, Franklin, that you might be interested in, that goes along with somewhat the deformation of the field, like Hans is talking about. I don't necessarily advocate to necessarily the source of the shock front that he's talking about, but the characteristics of the shock front being gravitational and being massive. You can demonstrate that to yourself kind of by looking at putting an object on the surface tension of a water. And if you pull on that object, you'll notice that there's a certain amount of resistance to it moving across the surface. And again, you'll have to have a light object that doesn't have a whole lot of weight to it. And then if you pull on it, you measure how much energy it takes to pull it. And then if you start bobbing that object up and down on the surface to create these shock fronts that like Hans is talking about, but you just want to create the shock fronts as much as possible on the surface of the water and not go too much in depth, because that will destroy the tension characteristic. If you do that and then you again put a sideways force or a lateral force on that object and see, you'll notice that it takes more energy to move that object through the surface than it took when it wasn't bobbing. And that's because of the pilot wave characteristic, where the wave is actually holding that. The wave is interacting with subsequent waves, is acting as subsequent waves. And because the waves are compressed in one direction and rarefied in the other direction of the direction of motion, it'll have more of a tendency to hold that object in the middle of the bobbing pattern, which equates to basically an inertial and mass type characteristic in a unified field. So you can do that yourself. If you said you have to have a very small object, find a way to bob it and disturb the surface tension as much as possible, because when you disturb the depth of the water, you get a whole different characteristic.
So where do you come down on this question of the fundamental question of what is matter? Now, you can say that you don't know, or you can come up with a specific conception of it.
I think what we just described, although it's in a single dimensional plane, is the pattern of waves, spherical waves, circular waves here on the surface, the spherical waves in space. That pattern of waves creates the characteristic of inertia and the characteristic of mass within the unified field, and that essentially is matter. It is a wave pattern that has the characteristics of inertia and has the characteristics of mass, and that's how we identify matter, is by its properties, its interactive properties. And so that basically what we just described with that bobbing characteristic, if that occurs within the unified field, the tensionable field that's three-dimensional, then you wind up with that characteristic of inertia, characteristics of mass, and even the characteristics of gravity. If you look deep enough at the characteristics of subsequent waves within this pattern, they're all there in that tension field. And as long as you have those characteristics, then you identify the center location of where that characteristic is coming from as matter, because that's how we identify matter, is by its characteristic interaction with us.
So you left out one property, which I think is very important.
What property would that be?
Solidity. Matter cannot pass through each other.
Well, waves can pass through each other.
Yes, that's the problem, that waves can pass through each other, but matter cannot. This is one of the things that I feel the wave explanation does not explain very well.
And that's because you're not looking at the entire wave characteristic. You're looking at waves that are going in opposite directions of each other. If you were to look at two wave fronts that are following each other in the same direction, but in close proximity to each other, you will notice that the leading wave front and the trailing wave front will actually have an attractive characteristic where they're trying to combine with each other. And that will mean the leading wave front will actually seem to have a tendency to slow, while the trailing wave front will have a tendency to increase. And eventually those two wave fronts will combine and travel together as a singular wave front. And I've given you the example a long time ago of two bubbles on the surface of the water and how they would attract each other due to the fact that when those two bubbles distort the surface tension, they actually create more tension in the surface when they're individual bubbles than when they're combined, because the volume under the individual bubble, under the single bubble, is the same as the volume under the two individual bubbles, but the surface area distorted by those two volumes is decreased. And the same is true if you were to take a string of bubbles and just line them up along line, or if you were even to take a toothpick and lay it on the surface of the water, and another toothpick and lay it on the surface of the water. Those two toothpicks, again, will attract towards each other if they get close enough and combine, just like two wave fronts in the surface that would be traveling combinatorially in the same direction, not opposed to each other, because they will increase and decrease and pass through each other in that direction. But if they're traveling in the same direction, they will actually combine. If you take that and you work that in,
these are all examples of attraction. How
that's
about
correct.
two electrons?
That is absolutely.
What are they doing?
Now, you're jumping into electrons, okay? We're going to stick with mass, gravity, and what is matter, because if you want to jump into electrons, you're getting into a more complex rotational pattern that occurs yet. And if you don't understand the basics, then there's no point in going clear into electrons. Two neutrons even will appear to repel each other if they get close enough. But the first thing you need to understand is that waves do not simply pass through each other, and you need to understand why. Then you start needing to work into how spherical patterns, repetitive spherical patterns, can interact with each other and actually attract each other. And once we get to that point, we can just start discussing how you can get further and further into that, and where these patterns can actually get to the point where they look like they are repelling each other. It's still all about attraction, but it's a matter of fact now that the attraction is not between the two, and in actuality, the attraction is not really between the two in the first place. The attraction is actually surrounding the two patterns, and that general characteristic of the two patterns in the field cause them to move towards each other. In the case of when they get close enough, that attractive force actually becomes stronger towards the outside of the two patterns, and they appear to move apart because of repulsion. But in fact, it is like Mach's principle. The universe is pulling them back apart because they are extended patterns out into infinity, and so they are part of the entire field.
I think there's a more traditional model that that we could look at. It's an Einsteinian model, the E equals mc squared. In that math, anytime we have an equal sign there, theoretically, algebraically, we should be able to move the operators from either side of the equals sign. And if energy equals matter times the time constant or the speed of light here, then matter we should be able to move matter or the velocity of the speed of light to the opposite side of the equation to define matter. And at this juncture, when individuals, when Albert was talking about the loss of mass, we can never create or destroy energy or mass. It's just we can only convert it from one state to another. And if mass, anytime we combine two entities, it requires energy to create that bond. And or if we're fusing together, that's why the term cold fusion applies, because anytime you're making a bond or joining something, we have to put in energy, or it requires energy from the surrounding. You can never have hot fusion. When you break the bonds, you release energy. And what happens is that in a misconstruction or misperception, we can confuse the release of energy with the loss of matter, because we're no longer able to quantify the smaller entities that remain after the bonds are broken. And then conversely, when we were discussing about waves of energy, when you have two waves of the specific frequency, that's where we end up with bucking electromagnetic fields, etc., and that's where we end up. That's where we have heating, etc., that causes the release of energy. But when you have two waves of different frequency, they pass through each other quite easily. Now, if you have a mass of sufficient density that oscillates at a different frequency, then something of the same mass, it's just in same construction that's not oscillating at the same frequency, is it possible for one of those mass to pass through the other? Because theoretically, it's composed of atomic structures, and if the lattice of the one is allowed to pass around and through the lattice of the other, then that which appears to be solid to us, to the naked eye, which really isn't, it's just construction of smaller nuclear components, then some of the presuppositions, and I'll use the term made by the allegations of an experiment conducted aboard a ship up in the Northeast a few years back, where they used a supercharged capacitors with the degaussing field to cause everything around it to oscillate at a different frequency, whereby with which when they allegedly finished the experiment and individuals had partially passed through solid metal bulkheads and expired right in front of the observers, and at one point the vessel even disappeared because it was out of phase with the existing frequency of the surrounding observers, and I'm saying the observer because it never left and never went anywhere. They later determined that it was they allegedly determined that it never went anywhere, that it was still there the whole time, but it was out of phase and just not visible, as stated by some of the alleged participants that were on board the ship and the ones that were off board ship. Just two thoughts for consideration.
Well, I kind of put that somewhat in the category of science fiction and somewhat kind of science fact. There is a situation where waves of a different frequency will more easily pass through each other and will not necessarily gain. The thing about the waves that we were just talking about, that are the waves that are fundamental to the neutron or fundamental to matter, there are basically volumetrically resonant spheres that are resonant to the tension characteristics of the carrier media. So basically all neutrons and all matter is going to be basically vibrating and resonating spherically towards a point at the same frequency. The wavelengths, however, can vary as you get farther and farther away from that point or closer to the point. The closer to that point you get of the center of the neutron, the shorter the wavelengths will become as it will move slower. The farther away you get, the longer they will become, and that's a characteristic that I mentioned also to you before, Franklin, because you have that experiment that shows when you have two vibrating objects, they will attract and repel each other according to half wavelength distances. That attraction or repelling each other happens at an incremental distance because you're using a media and a characteristics where the wavelengths don't change, because you're not stressing the media's non-linear characteristics of elasticity enough. But if you stress the media's non-linear characteristics of elasticity, like in any media, when you stress it, it will have a certain tension at one stress level, and the farther you stress it, that it may become stronger or it may become weaker. When you get stressed it enough and you get to the point where you get the maximum tensile strength, it will start to become weaker, and as it becomes weaker, waves will have a tendency to travel through it slower. And that all coincides with as these waves diverge away from the focal point, the media will actually be stronger because there will be less disturbance, and so over the distance the waves will actually travel faster. that allows these two wave patterns, if you will, if there's two of them within the media, to attract each other regardless of whether they're at a half-length distance or not, because it's the integration of all the waves, not just one or two waves that are the same length.
Yeah, I mean, it's interesting. I mean, we have this whole thing about we have things which we think are waves, and then we have things which we think are matter. Now, mainstream would usually say that if you have waves, that they're waving in some sort of medium, but we wouldn't say that the wave itself was any form of matter. So that is the usual way that we look at things. So if we have water and I wave my hand in it, I mean, then definitely there's something that's moving at specific speed which has detectable energy. But we would not say that, but we distinguish that between the molecules of the water, which we believe is actually matter. Now, you know, what Cornelius and others say is that the actual wave actually does become what we observe as the matter, which is like, you know, hydrogen or whatnot.
No, you're correct. To be more correct, it's the pattern of the wave that establishes the characteristics of matter. To have a particle that has mass and has gravitational characteristics and has inertia, you have to have a pattern of waves that are totally spherical. You have another pattern of waves that can be changed to added to that can give it electrical characteristics. But it's the pattern of waves, and kind of Bill was alluding to that earlier too a little bit with the Russian experiment where you were heating and cooling something and it was changing its mass characteristics. And this would be indicative of if it's perfectly spherical waves, you have absolutely the maximum possible amount of mass density per unit area of space, because the mass characteristics and inertial characteristics are dependent on the spherical nature of the overlapping wave patterns. So if we have two of these wave patterns in space and they're both very spherical, they will overlap very well. If you look at the waves that are a distance from the centers of both of them, eventually those waves will get to the point where they perfectly overlap because of this progressively lengthening interwavelength distance. You have to get to a point where eventually the waves, if they both keep lengthening, then if you're maybe an inch apart, for instance, and the waves are an inch long or a quarter inch long or so, then as you get farther away, that quarter inch becomes an inch. Then eventually you get to where the wavelengths maybe are a foot between wavelengths, and your center of focus of each of those wavelengths is only an inch apart. So obviously each wavelength is now going to, at that distance, almost perfectly overlap. And so you get this attraction and tension. But it's the spherical nature of the wave that gives it the mass characteristics that we then call matter, because it has that characteristics of matter. It's inertial, it stays, it's kind of tied to one location in space, and to try to get it to move, it takes energy, or you have to distort that wave pattern. You have to distort that spherical wave pattern to get it to move. And so when Bill is heating something, you take a perfectly spherical wave pattern, which is cool and resonant, and you heat it, it becomes rippled on those waves. Each of those waves is no longer spherical. The less spherical nature you get, the less mass you get. It's kind of counterintuitive to what they're saying, well, E equals mc squared. Therefore, if you add more energy, it ought to become more massive. Well, you're adding more energy, but it's not necessarily becoming more massive because you're disturbing that resonant, that spherical nature of the waves, and they don't overlay each other and they don't follow each other through the surface one after the other very closely. So therefore they will not have nearly the attractive characteristic they have when they're perfectly spherical and matching each other back to back. And so you'll start to actually lose the mass characteristics or the inertial characteristics of it. And when you do that to a complex atom, which is a combination of all these waves, you can hit these points of, okay, now it becomes more massive and now it becomes less massive as you heat it up. Because certain wave characteristics from certain portions of that particle become more or less interactive and more or less overlapping. I think that's probably a lot to take in, so I'm just going to stop right there.
All right. Yeah. Well, it's all very interesting, Corey. I appreciate your contributions. But if we're talking about waves, I mean, obviously people will always ask, well, what is it waving in? What's the medium made out of? And I think that is a question that needs to be answered. Once again, getting on my own soapbox, if I believe that everything is composed of positrons and electrons, then in fact the medium itself has to be composed of positrons and electrons. And I don't think that's not too far an outrageous idea. A lot of people have presupposed that the space filled with a field of charges or something like that. So I don't think that's that outrageous.
Yeah,
but I think it is important that if we say there's waves, that we do define, what's it waving through.
It's simply waving through a tensionable media. There's no parts to this media. There needs to be no parts. The only reason there needs to be parts is we have to be able to visualize, how can we see this tension wave? How can you see a tension wave moving? If I put those two bubbles on the surface of the water and I look at those bubbles, they appear to be attracting each other. They're going towards each other, but I cannot see the tension within that media that's creating that attraction. If we go down into the ether and down into the most fundamental thing where there are no parts to it, there is only this tensionable media, then all there is the tension. And the only way we can see that tension being there is if we create two areas of tension which are these two resonant locations of tension patterns that can then interact with each other, and we can observe that this tension pattern, which I'm a part of, moves closer to that tension pattern. But there is no actual particulate media to it. It's a continuum of media that is tensionable, can be stressed. But if there's no parts to it, you can't really see it until it becomes uniquely distressed, or uniquely stressed, and then you can see the characteristics of those two different stressed areas interacting with each other. Only because you are part of that. You are also nothing more than a stress pattern within that field.
Yeah, so while I can totally appreciate that, and while we can kind of see that, it just took you like 3 minutes to explain that, versus, that's, because, your explanations are quite complicated, and you take quite some time to explain, and I'm not saying you're wrong or anything, but they are kind of complicated to explain, versus things which we are more familiar with, which are particulate medium, like water or air. That doesn't take me but 2 seconds to explain that, we're just in a positron-electron sea.
But
that's something
that people immediately relate to.
Right, and that's fully understandable, and that's why I had to use, for instance, the example of tensionable media being the surface of the water, which we all know is made of particles, but you have to concentrate on not what the media is, because that's what allows us to visualize it in our normal interactive world of thinking. But when you actually think about deep down inside what creates that electron, what's creating that positron of the sea and stuff like that, what is that made of, then you get to the point where you just look at, the tension is what's doing all the work. It's the tension that's there. And so that's why, yes, I understand. I mean, we all have to use analogous examples because that's the reality of what we're used to in our world. And that's why, that's the only way I can describe it to anybody is you always have to relate to something that people can relate to.
I think that in the world, if you try to discuss something hidden, it's there, but you claim it's hidden, it will naturally take likely a longer time and be a little more complicated than trying to explain something that isn't hidden, because that may not take any time at all because it isn't hidden. But I wanted to say this about what Franklin is saying. I think that you can do a lot with positrons and electrons and so on. But another fellow raised the question: exactly what is this what is positive and negative in our world. Can we go beyond that useful paradigm? Maybe even should we? And I just want to remind people that there are structures in chemistry, such as a left-handed molecule and a right-handed molecule. The molecules are entirely the same. It's just that one is left-handed and one is right-handed, and therefore you cannot get them to match. Uh, uh, to match up by putting them together. As I say, they're mirror images. So I use that analogy because when we discuss positrons and electrons, there may be a cause as to why something is a positron and not an electron, and why something's an electron instead of a positron. And I just think left-handed molecules and right-handed molecules are an example of something that they're the same mass or the same weight. They're made of the same things. It's just their structure and their geometry are the only things that make them different. So
okay. Carl, we can go. I can go back. I think that goes back to what I was saying last week. But I noticed Hans has his flag raised, so I think I'll let him speak if that's okay. Franklin?
Yeah, go ahead, Hans.
Sorry, I would have needed to put my flag down again. Again, I want to suggest that if you want to go to the origin of mass, really to the origin of gravity, then you have to look at very tiny things. You have to look at point-like triggers of the field. They can already deform the field. If you study that, then you find the origin of gravity and the origin of mass.
Yeah.
Well, getting back to, the main question here, like you said, is like, what is this electron? What is this positron thing?
Okay, I think remember last weekend, Franklin, where we were speaking about the characteristics of a electron and a positron, and I was speaking about, now this time I told you that about the characteristics of the neutron and the mass. And last weekend, if you remember, I was talking about the circular nature of a revolving or spinning item, a spinning piece of mass. And it's like when you take this spherical pattern that I'm talking about, this mass, and you put on it a cam-like lobe. Instead of being perfectly spherical, you put it into a cam-like lobe shape, and you begin to rotate that cam-like lobe shape around that sphere. And of course, subsequent spherical waves that are out there will follow that same cam-like lobe pattern, only farther out in the larger lobes. Because the waves are larger, but you're still rotating that lobe around that sphere, around that point. And what we were getting into, and this gets into the left-hand, right-hand rule thing, is it's not just spinning around in one plane, it's also rotating and spinning in a second plane. And when you do that, then you get away from this, if I look at the clock from the backside, it's clockwise, and if I look at, counterclockwise, if I look at it on the front side, it's counterclockwise. It is, no matter how you look at it, always going to be rotating in a clockwise direction. So it's always going to be that one-handed situation. So electrons are this lobe-like pattern that's processing in a clockwise direction, and positrons are exactly the same pattern, but they're processing in the counterclockwise direction. But we live in a world where the universe is processing in a counterclockwise direction. Therefore, all electrons within it are processing in a clockwise direction. And so our world is primarily electrons and not positrons. We can create these counterclockwise processing patterns momentarily of positrons, but they will be overtaken and annihilated by the fact that they're in a universe that's also spinning in the wrong direction, so they won't last. And in Bill's case, where he spoke of the neutron, we can create the neutron outside of the atom. But a neutron is a non-spinning spherical pattern that's outside, that's in this universe that has a counterclockwise spherical precession to it. So the neutron is not going to last very long. As you all know, its decay time is very quick. The same thing about a neutron coming out of an atom. There's no evidence of the neutron coming out of an atom, and that's because the atom already has this pattern of precession within it. So you're not going to get something that's not spinning coming out of something that is spinning. However, you can create something that isn't spinning and put it within a universe that is spinning. That's not, actually, you can create something that's not spinning and put it in a universe that is spinning or processing, and eventually that object will acquire the precession characteristics opposite to that environment, and that's why.
So this is the idea that the charge is related to a direction of spin. Now,
that's correct.
I think Bill Lucas's idea is probably also similar to that.
I've said that before about Bill Lucas's concept of his toroidal waveform, but his toroidal waveform, unfortunately, that he shows is a pattern that's more like an electron that is linearly propagating through space because it has a polarity to it. When you're a toroid, you can look at the toroid from the front, back side, and the back side, and they'll be spinning in opposite directions, much like the clock. So it still has a polarity to it, and that's because a moving electron has a magnetic field which does have a polarity to it. A static electron will not be toroidal in shape, but rather will be a waveform that is like the lobe I'm speaking of, that is processing continuously in one direction around this globe, around the sphere, and it's doing so in such a fast manner that it's like a spinning propeller. To us, it looks like it's an evenly distributed electrical field in all directions. No matter how we look at it, it looks the same because its charge is revolving so fast that it looks like a solid charge. And charges can revolve fast because charges don't have mass. Remember, the mass is the spherical part of it, and the charge is the alternate, just like the dog chasing its tail part of it going around this mass.
Yeah. Now my problem with that, any kind of explanation that charge is some kind of rotation, is that, like a hurricane, it actually has to push around whatever it's rotating to great distances, and the electrostatic field extends to infinity.
But it's a field. The field itself doesn't have mass. The mass is within the spherical pattern, just like light doesn't have mass. Just like light does. It does extend, but it doesn't have mass. It just is a wave pattern moving through space. So you're talking about just like a hurricane, but a hurricane has mass. The particles moving around have mass. The electron, the charge, like the photon, doesn't have mass. It's simply a distortion of the media.
Yeah, and that distortion, like if I have an electron in my hand and it's rotating space that way, that all the way in the moon, way out, it still has to, in order for its influence to be felt, it still has to be moving it towards the right.
That's correct.
At millions of miles per hour because it's so far away.
Just at the speed of light.
A thought on the mass.
I find that hard to believe.
It's just at the speed of light, and it doesn't.
You can see the main problem here is that I don't see how a charge could propagate for very long if it's in any kind of field.
Right.
The only thing that I know of where an electron could go that distance is like an electromagnetic wave. We know an electromagnetic wave emitted from here on the Earth, easily received on the moon.
Well, that's what it is. It's an electromagnetic wave. That's what the charge is. but it's going to take time to get all that settled in. I mean, I don't expect anybody to be able to visualize all of this in a very, very brief one sitting time. And I wasn't even going to approach the electron and the charge characteristics because of the depth in which you have to be able to visualize these things if you're just becoming familiar with them.
Yeah, so I mean, like I said, that was one of my other criticisms, and that perhaps you can explain these things, but there's no way you're going to be able to explain it in an hour, even.
Well, that's not a criticism. That's just a reality and a fact.
No, I mean, because I can explain how my electrons work in like a minute, right? Because all I say, well, first of all, I have to say, I still don't know exactly what an electron and positron is. I'll make that clear. I mean, some people will say that it's a specific toroid ring. I haven't really found a physical structure for the electron that makes me happy. So I'll just say that we know they're there. Of all the things that we know, I think we know that a positron and electron exists, and we know what their physical characteristics are. We can isolate them in space. They exist. And so that's where I kind of, that it's my monad, that's the uncuttable thing, that fundamentally I would say in my own explanation, what matter is whatever these electrons are.
Right.
And I may not have the great explanation of what they exactly are. My explanation kind of ends at that point, but I would disagree that they are involved in any kind of wave phenomenon. I would disagree, and once again, that's my own personal opinion. That I feel that when you take something which is physical, and as the Greeks did, you cut it up until you get something that eventually you'll still get to something that has the same properties as what you started with, which is a hard little ball that takes a finite amount of space, has a surface area, is not made out of a wave, and is as physical as the little brick I'm holding. That's just kind of my supposition.
Oh yeah, but we are going deeper. We're trying to make the connection between energy. You're trying to make the real connection between E equals mc squared and define where the connection between energy and mass is.
Well, we haven't even gotten there.
We actually just did finish getting there. I just explained that to you.
Gentlemen, I think I can propose a simple model that helps that understanding along. Water, if we extract all the energy from it, is a solid like ice, or as much as energy as we can. If we added a little more energy to it, it changes media, it becomes liquid, and waves travel much faster through that than does the solid like the ice. And then if we add more energy to it, it becomes steam, it becomes a vapor, and in space, you can actually transmit audio waves through that. And if we continue to add more energy to it, you can actually create the equivalent of an atmosphere in space. And waves travel much better, and they travel bidirectionally for it. But it's all a function of how that particular molecular structure changes the form from what we would consider a solid mass to all the way through to an atmosphere, just with how much energy is in it.
Okay, that's an interesting point, but I'm not quite sure how that.
Question for you.
You saying something, Bob?
Yeah. What happens to your solid?
I'd like to ask a Lucas question, please.
When an electron and a positron come together and it disappears into energy, what has become of your fundamental solid thing?
Okay, that's a very good question. So, on one hand, I have an electron. On the other hand, I have a positron. Okay, they come together. Now, I explained that because these things are oppositely charged, they're going to start accelerating at each other. I mean, they're going to gain their fastest speed as they approach each other. And the fastest speed they can go is the speed of light. So these things are going to collide together at the speed of light. So this has what? What's the kinetic energy of this particle then? Kinetic energy is 1/2 mv squared. And what's the kinetic energy of this particle? 1/2 mv squared. Or in the case of if these things actually attain the speed of light, 1/2 mc squared. So this particle has 1/2 mc squared. This particle has 1 mc squared. So what's going to happen when they see two things collide together? They're going to come together at high speed, just like my hands come together. Now the kinetic energy of my hands is released in the form of sound and heat. My hands did not disappear in the process. So similarly, when the two particles come together at the speed of light, the expected, and they stick together in an inelastic collision, the amount of energy you expect to be released, just like when I clap my hand, is going to be 1/2 mc squared plus 1/2 mc squared, which is, guess what? mc squared. So mc squared is the expected kinetic energy that we expect to see out of a collision of two positrons and electrons. And what happens to the positrons and electrons? I believe that they just glue together, and they are there. And the only reason why we cannot see it is because they are surrounded by a sea of identical particles. It's as if I had reacted some hydrogen and oxygen molecules in a glass of water, and you would see, oh, yes, it created some energy, and then it's disappeared. But it hasn't disappeared. It just became a water molecule, which you cannot see individually anymore because you can't tell the difference between that one and the existing sea. So, Bob, what do you think of that explanation? That is my explanation. There is no conversion of matter to energy. The only thing we're seeing in E equals mc squared is the release of the kinetic energy from the collision.
Franklin, in the analogy of nuclear fuel rods, when you remove one from a reactor, it weighs significantly less than it originally did, that's not a process of particulate in the bottom of the reactor. The fuel rods physically weigh less as the energy is released. So there is one example of with energy being released or something converting to energy that it weighs less.
Well, definitely we know during nuclear reactions, all kinds of things come out. Certainly lots of neutrons come out, and those weigh matter. I mean, those definitely escape the reactor. Electrons come out, those are matter. Those definitely escape the matter. I mean, there's a lot of things that escaping the reactor that don't end up in the bottom of the reactor, definitely.
Franklin, I kind of like to respond to that, but I think Harry has been trying to say something too, and I think I have sent out an email defining what happens when electrons and protons meet.
Yes, Harry, please go ahead. Go ahead, Harry. You've been trying to say something, I think. Hello?
Bill, this is Harry. Question for you. You didn't talk about the role of space in the monad theory. As the materialist idea was that the world existed of monads and the void. Tell me what the role of space is in your theory, or what you're saying. You understand?
Okay, I'll try to comment on that. First of all, in terms of the shape of the electron, I want to mention this first. The electron has two magnetic properties. It has a spin magnetic moment and a regular magnetic moment. And so you have to have two types of motion that are in the electron. And those motions, if you have a toroidal ring, it's not just moving around the circumference of the ring, but you also have to have a second rotation, which is around the cross section of the ring. So that makes a distinction, and the spin and the magnetic moment of the electron are two very well measured properties that have to be explained by any model of the electron. Okay, now
Bill,
getting back.
I don't disagree with that. I'm just saying that when the electron is static, the shape of the toroid no longer exists. There's still the two spins because that's what the precession is about. But because there is no from the outside world, the electric field is uniform in all directions, and there's no magnetic characteristics to the electron unless it's moving linearly. That toroidal ring is now collapsed into a spherically moving pattern of waves around the sphere, and there's no longer a toroidal shape. The toroidal shape comes into play when you are within the shell of an atom, or when you're moving linearly and you get the electromagnetic characteristics out of a moving electron. So that's my comment on that. But
I don't think that's true, because when I was in graduate school for my PhD, we did electron-electron scattering, and the scattering occurs and reflects both the magnetic moment and the spin at large distances.
But the thing is about the scattering, they're still moving linearly when they're scattering, so they have that magnetic characteristic to them while they're moving.
We did scattering at less than 1 electron volt.
It doesn't matter. They're still moving, so there's going to be less
They're
of a
moving
magnetic...
less than they move in an atom, according to the theories of the atom.
But there's still a magnetic field if they're propagating linearly, so they are still not spherical.
Yeah, but that's the slowest we can. Well, also in the penning trap, you can measure it there too, and they're not moving at all.
No, I think they are. They have to keep them in oscillation.
Yeah, they're vibrating back and forth within there. They're certainly moving within a penning trap.
Well, the penning trap, you try to balance all the forces out and then make your measurements. So that's how we measure the spin and the magnetic moment to highest accuracy, is in something like the penning trap.
Right, but like I said, anyway, let's go on with what you were going to.
Getting back to what space is, the idea for the formation of the universe, for instance, is that you have a source somewhere of the electromagnetic field. And then as disturbances occur in the electromagnetic field, you create solitons, which are kind of like semi-permanent standing waves in the electromagnetic field. And those are your monads. And then the monads get together and form elementary particles. The monad itself is not an elementary particle as far as we know. And
unless it's an electron.
So anyway, when you do this model, you have to be able to predict what is the complete set of elementary particles as a function of energy, and what are the masses of those elementary particles. Okay.
That's kind of going beyond what is space here, Bill.
Yeah, but I'm just trying to point out that we have been able to do that. We've published it, Russia and in Spain, but not here. I'm putting out a book on that. So the standard model of elementary particles requires 19 to 29 adjustable constants to explain the properties of elementary particles. We have no adjustable constants. We do it entirely from electrodynamics, and we're able to show that the different geometrical combinations, structures that make the various elementary particles, determines the mass also, and the other properties of the elementary particles, the way they decay, the way they react with other particles when they're collide with them. And so that is something that every model eventually has to be able to explain. So I just want to make that clear that it's a big problem.
Goes to this. Bill.
Go ahead.
My question to make it more, is space just the electromagnetic field, or is it something different in which the electromagnetic field exists?
Okay, the electromagnetic field pervades all of space, and in between big structures like galaxies and stars and stuff like that, you still have a small amount of hydrogen, helium, and other elementary particles. And they are. Pardon? Say again?
Yeah, we can't hear you, Harry. Maybe you need to
I don't
put
think
your
anybody
question.
said anything.
Oh, yeah, we're
Sorry about that.
okay. Well, we're kind of getting towards the top of the hour. So, Alistair, you raised your flag. Did you want to? Do you have a comment?
Yes. Gosh, when we are talking about existence and gravity, one of the things we should keep in mind is that all things are always in motion. So when we talk about static, we really talk about unified motion, not about actual lack of motion, because when something comes to the earth and it's at rest, it's not at rest, it's traveling with the earth. Gravity itself is not a come to me, it's a come with me. So when we throw something in the air, it's no longer traveling at the same rate and direction as the earth, but it comes back to the earth. But the earth itself is in motion. And when that object comes back to the earth, its motion comes unified with where it comes at rest. For example, something that goes up and down and lands at the equator is going around the earth with the equator, but if it goes up and down at the pole, it's not going around. Instead, its orientation, how best to put it, if because the earth is traveling northwards, the object is now traveling, it's rotating on the North Pole, but traveling with the earth versus it's different than an object on the equator. So when we think of gravity and static and mass and motion, I just want to put it out there. Think of gravity as come with me, not come to me. Come to my come towards my motion set. And you have to see all the different parts of the motion set, which include a rotation, include an orbit, and include a trajectory. Is that sensible?
Well, that was something that was completely different, I'm sure. We weren't talking too much about gravity, I don't think.
No, but we're talking about, we mentioned static, and static is lack of motion, but there is no lack of motion.
Well, that's certainly true.
I think we all understand it's pretty much a relative static. Anyway, it looks like you're going to summarize your.
Yep, we're getting towards the top of the hour. So the initial topic here, which is what's the matter?
I want to know what Bill's answer is to my question. What's Bill's answer to my question?
So your question is,
what
is
Bill's answer to my question about space?
Yeah, your question was, though, what is the electrostatic field made out of? Or is space the electrostatic field? Is that your question?
No. I want to know whether or not, what in Bill's theory is the role of space? Is space a carrier of the electromagnetic field, or is it the electromagnetic field itself?
Okay, Bill, he's giving you two choices. What is it?
Space is the electromagnetic field, and I happen to be from a Judeo-Christian background, a Christian, and in the Bible,
I want to know.
Let me finish. In the Bible, God is the source of all electromagnetic fields. And he creates by disturbing the field to create monads, which produce matter and that sort of thing. And so that's the big picture. If you leave the religious part out, you have a question of where does the electromagnetic field come from if there is no such thing as charge?
So, Harry, does that answer your question?
Well, Bill, you seem to be saying that the space. No. You seem to be saying to me that space is really the electromagnetic. That's what it sounds like to me.
Yes, that's all there is the electromagnetic field. There isn't anything else. There's standing waves
Thank you.
called solitons.
That's what I thought you were saying.
Everything is made of the electromagnetic field.
So there is no space. There's only the field.
Yeah, but we call it space because we don't see any structures there. And we call it a vacuum because we don't see any structures there, or very few structures. And so that's the view that we typically take.
Yeah, I think Bill and I agree on that respect. I don't call it necessarily an electromagnetic field, but it is the same thing. That's all there is.
Some fundamental something or another.
Notice how each of us has certain aspects of our work and our development theories in common.
Thank you, Bill, for answering.
And that's because there's a certain commonality in all these fields. And if you look at quantum mechanics, for instance, what is it? What is the vacuum there? It's something like a field, and they're creating and losing particles in and out of the field, and so all these approaches to science have something in common, but they are not all equally complete. And so that's what needs to be done. And so in my work, I feel like it's not complete unless you can explain the complete set of elementary particles and their properties from electrodynamics alone. So that's what I'm trying to do. And I think I have done that for elementary particles, and I'm in the process of writing the book and showing that and publishing it. And but like, for instance, take the work of our moderator. If the electron and the positron could be your monads in a sense, and you can make everything out of them. And so there's just so much in common with each of the different ones, but they're different in other regards. And so it's the completeness of your explanation that's going to, and the simplicity of being able to explain so many things, that will be the important parts of our work. And one of the things that we get out of these meetings is we get exposed to more and more things that you've got to be able to explain. And that's a good thing. And sometimes you have to check out the veracity of the experiments, because maybe they're not good. Maybe they don't measure what they're supposed to, and all that kind of stuff. So that's something too. You have to take a very critical view of all the experiments to make sure that they are really valid. And
yes, I mean, I think what's good about the discussion is because I don't think any group of mainstream people would touch this question, which is what's the matter, with a 10-foot pole. Because if they did, they'd have to all sit around, scratch their head, and say, I haven't the slightest idea. And so, it's interesting to hear the different things that people have said. So, I mean, we've heard certainly at least 3 or 4 different things. So, we've heard about the work of Winston Bostick. And, we just discussed that, that space is this electromagnetic field, and that monads are made of electromagnetic fields, and then everything is made out of monads. So that's one possible explanation. I think Hans shared that he believes that matter comes in the form of shock fronts. And we also heard from Cornelius that matter is a specific wave pattern in perhaps, out of whatever this field is. And you've heard from me, which is that I think matter is just electrons and positrons. I know someone put in the chat phys Lego, and yes, my goal, my bent in science is to explain everything absolutely in terms of Lego bricks. So maybe I will go down in history as being that silly person. But hey, everyone's got to have their bent, so that's mine. And
I was the first Lego.
Yeah, that's funny. I may have to adopt that. I may have to
Sorry.
make a whole Lego, make a whole website just with that title. That's actually kind of interesting. But I think this is largely motivated on this whole E equals MC squared matter equivalence thing. So people are trying to find some way to take something that's ponderable as a Lego brick and turn it into energy, which is motion, which is like waves. So, but I think that I made the point that I don't believe that ever happens. I don't believe that matter is ever converted. I mean, they were saying that, well, matter is an energy can neither be created nor destroyed, but they're converted. And I personally think that conversion is also a destruction of matter and energy. So if you have a conversion of matter and energy, that would actually be a simultaneous violation of the conservation of matter and energy. And I really don't feel that two wrongs make a right in that case. So that's why my bias is to explain everything in terms of a Lego brick, which remains a brick, is not made out of wave, solid, takes up space. That was my point. But I can see where, yes.
If you take your Lego brick and accelerate it to the speed of the velocity, the speed of light, and aim it at something, that has energy. So energy equals your Lego brick times the velocity of the speed of light.
That is absolutely it. And if I accelerated my Lego brick to the speed of light and aimed it at the planet Earth, it would explode with the force mc squared, and it would go off like an atomic bomb. But the Lego brick itself would not disappear. I mean, that's the idea behind these kinetic energy impactors, that they send down this telephone pole at some humongous velocity, and when it hits the Earth, it's going to go up like an atomic bomb. And so there's no conversion of matter to energy there. That's just the release of the kinetic energy.
Or that's a discussion for another day.
That sounds exactly like what I was going to say. I think that's a discussion for another day.
That's right. We could probably discuss E equals MC squared all by itself. But I believe that does it for this discussion about what's the matter. Now, I really didn't think that we would ever come to any conclusion, because we're basically talking about stuff that we can't see. So it's all a matter of hypotheses and suppositions, and it all shows our basic biases about how we would like to think about the world. Some people like to think about a shock front, some people like to think about wave patterns, some people like to think about monads, and some people like to think about Lego bricks. So, but it's up to everyone to decide what they think, and that's what we're here for, just to spread out different ideas. So that will do it for this week's science chat. And yes, we will do this again next week on the 18th. So I'm going to end the